4.6 Lesson 1, Differentiability and Continuity. Our objectives today are you will understand the relationship between the differentiability of a function at a point and the continuity of the function at that point. And you will be able to use that relationship to determine the differentiability or continuity of a function at a point. So vocabulary, what does it mean for a function to be differentiable? We can talk about differentiability of a function at a single point. And what does it mean for a function to be differentiable? That means the function would have to be differentiable at every point in its domain. Every point in its domain. Continuity, we will review what that means. And then when we look at the statement that shows the relationship between differentiability of a function at a point and continuity of that function at that point, that relationship is given as a conditional statement, P implies Q, with a hypothesis and a conclusion. The contrapositive of that conditional statement is not Q, implies not P, and you may remember that a conditional statement and its contrapositive are logically equivalent. If we know one to be true, the other must also be true. However, the same cannot be said for a conditional statement and its converse. If you have P implies Q, Q implies P is called the converse. The conditional statement could be true, and the converse could be true or false. They're not equivalent, they're different statements. And the inverse of a conditional statement is not P implies not Q. And the original conditional statement could be true, and the inverse could be true or false. They're not equivalent. This is the relationship that we want to learn about today. If a function f is differentiable at a point, then it must also be continuous at that point. So that's a conditional statement, P implies Q. Its contrapositive, not Q implies not P, is logically equivalent to the conditional statement. And because the conditional statement is true, the contrapositive must also be true. And the contrapositive of the property states you switch the conclusion and the hypothesis and you negate each one. So you're going to say if a function f is not continuous at a point, then that function is not differentiable at that point. So these are both logically equivalent and they're both true. But as I said earlier, the converse and the inverse of this property are not logically equivalent to the conditional statement, and in this particular case, they are both false. So what that means is the converse would be Q implies P, and the converse reads like this. If a function f is continuous at x is equal to c, then it is differentiable at x is equal to c, and that is false. It is not true that continuity implies differentiability. It is true that differentiability implies continuity, but not the other way. And then the inverse would be not P implies not Q. And this is also false. It is not true that if a function f is not differentiable at x is equal to c, then it is not continuous at x is equal to c. That's not true. You could have a function that's not differentiable at a point, but it could be continuous at that point. So what is this telling us? It's telling us exactly how we read it. If you know that a function is differentiable at x is equal to c, then it must also be continuous at x is equal to c, but you can't say it the other way around. However, the contrapositive is logically equivalent, and what that tells us is if a function is not continuous at x is equal to c, then it is not differentiable at x is equal to c. We want to think about why is this true, and we'll be taking a look at the proof of this property. And to understand the proof, you have to go back to the definition of the derivative of a function at a point, because in our property, that is what we call the hypothesis. We assume that we have a function that is differentiable at a point x is equal to c. What does that mean? It means this. This is the definition of the derivative of a function at a point. So if we know this to be true, how can we show that the function must be continuous at x is equal to c? What does continuity of a function at a point mean? It means this. This is the definition of continuity at a point. So the function must be defined at the point. The limit of the function as x approaches c must exist. And the limit of the function as x approaches c must be equal to the value of the function at c. This particular condition, it incorporates the other two as well. So this is good enough because it has all three of the requirements for continuity encapsulated in one. So that's how we show that a function is continuous. So if we want to show that a function is continuous at x is equal to c, this is what we have to show. But what do we know to begin with? We know by hypothesis that our function is differentiable at x is equal to c. So we know that this limit of the difference quotient f of x minus f of c over x minus c as x approaches c, the limit of the difference quotient as x approaches c exists. And if it exists, it tells us the derivative of the function at x is equal to c. So we start with this, and we have to show that this must also be true. And this difference quotient tells us the slope of a secant line passing through the 2 points c, f of c, and x, f of x. And when you take the limit of the difference quotient as x approaches c, it tells us the slope of the tangent line to the graph of f at this point c, f of c. And that is given by f prime of c. So here we have the proof of the property that if f is differentiable at x is equal to c, then f is continuous at x is equal to c. And as we just reviewed, what does it mean for a function to be continuous at x is equal to c? This is what we have to show that the function is continuous at x is equal to c. So to prove continuity of the function at x is equal to c, we have to show that this is the case by definition. What do we know to begin with? We know that the function is differentiable at x is equal to c. What does that mean? By definition, it means this limit must exist. So this is what we know to begin with, and from here, we have to show that this must be the case. So you can see this here, which is of course from the definition of the limit. It's from the definition of the derivative of a function at a point. For differentiability of the function at x is equal to c, that's what it means. And this is what we know by hypothesis. The function f is differentiable at x is equal to c. And then we're trying to show that this has to be the case. So look at how the proof is structured. We start with something that contains the limit f of x and f of c, because that's what we're trying to get to. And we do a step here, which is multiplying by a form of 1. We multiply by the same quantity in the numerator and the denominator, so we're not changing anything. We're just multiplying by a form of 1. But what that does is we started with this, and when we multiply by the form of 1, we can manipulate that algebraically to get it to be in this form. And this is, of course, a difference quotient. So now we're going to have the limit of a product. And because we have the limit of a product, we can write that as a product of two limits. So now what you have here is the limit from the definition of the derivative of a function at a point, which is of course f prime of c. And here you have the limit of this function x minus c as x approaches c. You can do direct substitution. When you substitute c for x, you get c minus c is 0. So this tells us that we have 0. So how does that help us to go from our hypothesis to what we want to show? And what we want to show is, of course, this. So our work here tells us that the limit that we have to begin with is equal to 0. And that's what we have stated here. And you will notice that here we have the limit as x approaches c of a difference. So you can write that as a difference of two limits. And f of c is just a constant, and the limit of a constant as x approaches c is just the value of that constant. And that is why we have it written just like that in the next line. So all we've done was we've written the left side of this equation in a different form. And of course, that has to be equal to 0. So that's what we write in the next line. And the next line after that, we just add f of c to both sides of the equation, and this is what we have. And that is, in fact, what we were trying to show, to argue that we have continuity. So we may conclude that if a function f is differentiable at x is equal to c, then it must also be continuous at that same point. So we just looked at the proof of this property. Prior to the beginning of the proof, we reviewed the definition of the derivative of a function at a point. We looked at what this difference quotient represents and what the limit of the difference quotient represents. And of course, we looked at the definition of continuity. We'd like to spend just a minute on this definition of continuity as a review, and then we'll look at examples relating to this property. You may remember from the fall quarter that we have these three conditions for continuity of a function at a point, because having these three conditions will guarantee that we would not have a discontinuity at a point. And of course, we need to make sure that all three of these are simultaneously true, so that we don't have one of the following situations for discontinuity. You can see from each of these three graphs that you have discontinuity at x is equal to c for one of three reasons. In the first graph, the function is not defined at x is equal to c, and the function f has what we call a removable discontinuity at x is equal to c. We would not like for that to happen, so we've got to make sure that the function is defined at x is equal to c. In the second case, the function is defined at x is equal to c. However, the limit of the function as x approaches c does not exist because the left-sided and the right-sided limits are not equal to each other. So this is what we call a non-removable or a jump discontinuity. So we've got to make sure that does not happen, so we also require that the limit of the function as x approaches c exists. And in the third case, the function is defined at x is equal to c, and the limit of the function as x approaches c does exist because the left-sided and the right-sided limits are equal. However, the value of the function at c is not equal to the limit of the function as x approaches c. So we can't have that happen either, so we require that the limit of the function as x approaches c is equal to the value of the function at c. All three of these must be simultaneously true for the function to be continuous at a point. And this third condition, as we said earlier, encapsulates all three. We take a look at example 1 from the textbook, and here's what we have. Prove that f of x is equal to x squared minus 7x plus 13 is continuous at x is equal to 4. If you were to try to do that directly by using the definition of continuity that we just reviewed, you'd have to show these three things. That the function is defined at x is equal to 4. That's easy to do. And then you'd have to show that the limit of the function as x approaches c, as x approaches 4 exists. And then you'd have to show that the value of the limit as x approaches c, in this case as x approaches 4, is equal to f of 4. There's also an alternative way you can prove that this function is continuous at x is equal to 4, and that is by using the property that we're learning today. Differentiability implies continuity. So if we can show that the function is differentiable at x is equal to 4, then by this property it must also be continuous at x is equal to 4, and that's how we'd like to do that today. So all we have to do is demonstrate that the function is differentiable at x is equal to 4, and use this property to conclude that therefore it must also be continuous at x is equal to 4. So how do we show that this function is differentiable at x is equal to 4? We can go ahead and use the differentiation rules that we learned early on in the course to find the derivative of the function. So you would use the power rule here and get 2x. You have, and then the derivative of negative 7x with respect to x is negative 7, and the derivative of the constant 13 is 0. So now you will go ahead and evaluate the derivative at x is equal to 4, and you get 2 times 2 is 4, minus 7 is negative 3. So what that tells us is that, let me back up a little bit. I'm evaluating the derivative at x is equal to 4, so I should have substituted 4 here instead of 2. I'm evaluating the derivative at x is equal to 4. So what I have here is 2 times 4 is 8. 8 minus 7 is 1. But what that tells us is that the derivative of the function at x is equal to 4 exists, and it is equal to 1, which means that the function is differentiable at x is equal to 4, and therefore by this property it must also be continuous at x is equal to 4. So because f prime of 4 is equal to 1, the function is differentiable at x is equal to 4. And by this property, therefore, the function is also continuous at x is equal to 4. Now we take a look at the second example from the textbook, example 2 on page 156. And here's what we have. Is the function g of x is equal to x minus 2 times x plus 3 divided by x minus 2, is that function differentiable at x is equal to 2? Justify your answer. The easy way to do this problem is to use the property from this section. Differentiability implies continuity. We have a conditional statement P implies Q. The contrapositive of that conditional statement, not Q implies not P, is logically equivalent to the conditional statement, and they're both true. So all we have to do is look at the contrapositive of the property, which states that if a function f is not continuous at x is equal to c, then it must not be differentiable at x is equal to c. So to answer the question, is this function differentiable at x is equal to 2, we can consider whether the function is not continuous at x is equal to 2, because if the function is not continuous at x is equal to 2, then we will know that it is not differentiable at x is equal to 2. And of course, is this function continuous at x is equal to 2? The answer is no, because if x were equal to 2, you would have a denominator of 0, and the function g would be undefined at x is equal to 2, and therefore not continuous at x is equal to 2. So because the function is not defined at x is equal to 2, it is not continuous at x is equal to 2, and therefore, by the contrapositive of this property, since the function is not continuous at x is equal to 2, it must not be differentiable at x is equal to 2. Now we take a look at example 3 from the textbook from page 156, and the instructions are: state whether the functions in the figure are differentiable or continuous at x is equal to c. We will begin by taking a look at the graph from part A, and here we have x is equal to c, and we want to know, is this function differentiable at x is equal to c or not? To answer that question, you go back to the definition of the derivative of a function at a point. And you're taking the limit of this difference quotient, which tells you slopes of secant lines through 2 points on the graph, one at c f of c, and a second point that is somewhere else on the curve, at x f of x. And that point could be to the left of c f of c. It could also be to the right of c f of c. And you're going to be considering this difference quotient, which tells you the slope of the secant line through the 2 points. And you take the limit of that difference quotient as the second point moves closer to the first point. If that limit exists, we say the function is differentiable at x is equal to c. And the derivative of the function at x is equal to c would give us the slope of the tangent line to the graph of f at c f of c. However, in this particular case with example 3a, this limit will fail to exist, and here's why. If you look at the secant lines when x f of x is to the left of c f of c, and what happens as x f of x gets closer to c f of c, the secant lines, the slopes of the secant lines will approach a particular limit. And that limit will be different from the limit of the slopes of the secant lines as the point x f of x approaches c f of c if x f of x happens to be on the right side of c f of c. So because the slopes of the secant lines will approach different values as the second point moves closer to the first, depending on if the second point is to the right of c f of c or to the left of c f of c, this particular limit will not exist because the left-sided limit of the difference quotient as x approaches c from the left will not equal the right-sided limit of the difference quotient as x approaches c from the right. And because the two one-sided limits of the difference quotient are not equal to each other, the two-sided limit from the definition does not exist, and therefore the function is not differentiable at x is equal to c. An easy way to see that visually is by looking at the graph that's given and observing that at x is equal to c, the graph has a sharp corner or a cusp. And when you see that, that tells you that this limit will not exist, and therefore the function will not be differentiable at x is equal to c. We still must consider whether the function is continuous at x is equal to c or not. In this particular case, our property will not help us. We can't apply this property because it can only be used if you know that the function is differentiable at x is equal to c, then you can conclude that the function is continuous at x is equal to c. However, the inverse, this is P implies Q. The inverse is not P implies not Q. This is actually a false statement. So if you know that a function is not differentiable at x is equal to c, it is not correct to conclude that it is not continuous at x is equal to c. It could be, maybe not. You have to find out differently. So we go back to the definition of continuity of a function at a point, and we check to see if all three of these conditions are satisfied for the function f at x is equal to c. So you can see that the function is defined at x is equal to c. The limit of the function as x approaches c does exist. If you're approaching c from the left of c, the function values approach the same number as the function values would approach if x were approaching c from the right of c. So the two one-sided limits of the function f exist as x approaches c, so the two-sided limit exists. And furthermore, you can see that the limit of the function as x approaches c is equal to the value of the function at c. So this function is continuous at x is equal to c. Now we take a look at graph B. You can see when you're looking at the graph that at x is equal to c, the limit of the function as x approaches c would not exist because the one-sided limits will have different values. So we can tell right away that the function g will have a non-removable discontinuity at x is equal to c. In other words, g is not continuous at x is equal to c. So what can we say about the differentiability of the function g at x is equal to c? We may use the contrapositive of this property and state that because the function is not continuous at x is equal to c, it must not be differentiable at x is equal to c. Now we look at part C, and you can see that the function is not going to be continuous at x is equal to c. The function has a removable discontinuity at x is equal to c. What we see is that the limit of the function as x approaches c exists. However, and the limit of the function as x approaches c exists, and the function is defined at x is equal to c. However, the values of the function at c and the limit of the function as x approaches c are not equal to each other, and that is why we have a removable discontinuity at x is equal to c for part C. And we know that if a function is not continuous at a point, then it is not differentiable at that point. We will conclude by taking a look at part D here, and the important thing to understand is the statement of the question. State whether each function is differentiable or continuous at x is equal to c. So you're actually looking at x is equal to c, which is right here. And you can see that the curve is smooth at x is equal to c, so that means that the function is differentiable there. When you consider a point x f of x either to the right of c f of c or to the left of c f of c, and then form this difference quotient to find the slope of a secant line, and then move the second point closer to the first point by letting x approach c, whether the second point is to the left of c f of c or to the right of c f of c, either way, this limit will approach the same value. And that's why the derivative of the function as x approaches the derivative of the function at x is equal to c would exist, and therefore the function is differentiable at x is equal to c. And the easy way to tell, just by looking at the graph that's given, is that at x is equal to c, the graph is smooth. So therefore the function is differentiable at x is equal to c. Contrast that with what we saw in part A, where at x is equal to c, the graph has a sharp corner, and therefore the function was not differentiable at x is equal to c. Since we know that the function f is differentiable at x is equal to c, then by this property it must also be continuous at x is equal to c. So today we looked at the relationship between the differentiability of a function at x is equal to c and the continuity of the function at x is equal to c. And we used that relationship to do some problems where we were considering the differentiability and continuity of a function at x is equal to c. Sometimes we couldn't use that relationship, and sometimes we could.